For years, the commercial EV market relied heavily on standard lithium iron phosphate battery chemistry, but the energy density of a standard LFP cell plateaus around 200 watt-hours per kilogram. To push past that limit, researchers at the Chinese Academy of Sciences recently engineered a high-energy solid-state pouch cell that hits 451.5 watt-hours per kilogram. That density is paired with an ultra-fast charging capability. At a 20C charge rate, the cell maintains stable performance through 3-minute charge and discharge cycles. This result is part of a broader race toward the 500 watt-hour per kilogram threshold. The Fraunhofer Institute maps the competing solid-state architectures into 3 distinct categories: Li-ox for oxide-based solid electrolytes, Li-Po for polymers, and Li-SU for sulfides. The 451.5 watt-hour breakthrough utilized a Li-Po architecture. Specifically, the researchers developed a compatibilizing solvent plastization strategy, introducing a volatile solvent during preparation that locks a stable plasticizer inside the polymer network to prevent degradation at the electrode interface. These milestones move solid-state technology out of laboratory theory into small-scale production and formal engineering validation. Moving toward commercial scale, solving the cell's material chemistry exposes a massive downstream problem. High energy density is useless if we cannot manage the physical realities of manufacturing and disposal. The immediate crisis is that our existing global infrastructure for recycling lithium-ion batteries is entirely unequipped to handle the highly engineered architectures of solid-state cells. Currently, the industry relies heavily on pyrometallurgy. This is a brute force approach that dumps spent battery packs into smelting furnaces. It demands massive thermal energy inputs to melt the components down into a mixed liquid slag. The main alternative is hydrometallurgy, submerging shredded battery materials into vats of highly toxic acids to chemically leach out valuable metals. Both legacy methods destroy the very thing that makes a solid-state battery valuable. We spend billions of dollars engineering precise inorganic solid electrolytes and complex crystal structures, only to throw them into a furnace or acid bath to extract raw basic elements. Standard lithium-ion batteries use volatile liquid electrolytes, making physical dismantling dangerous. But inorganic solid-state cells are intrinsically non-flammable. That missing fire hazard opens up an entirely different physical approach to taking them apart. Applying destructive recycling to solid-state batteries consumes massive energy to erase highly valuable engineering work. We need a process that preserves the molecular structure we worked so hard to build. To measure exactly how inefficient legacy methods are, we can look at data from the Everbat life cycle model developed by Argonne National Laboratory. These charts plot the energy consumption to recycle cathode material. The top bars show the massive energy toll of legacy methods versus the direct method's minimal footprint. Hydrometallurgy's penalty stems from sulfuric acid production, while pyrometallurgy's massive greenhouse gas emissions come directly from smelting combustion. Direct recycling operates on a different principle. Instead of melting or dissolving the cell down to base elements, it isolates and recovers the exact functional components without breaking their chemical bonds. The data proves that to commercialize SSBs sustainably, the industry must transition from elemental destruction to a direct recycling method that preserves molecular architecture. To see how direct recycling works in practice, we can look at a model using a sulfide-based all-solid-state battery. This cell pairs a lithium cobalt oxide cathode with a highly conductive solid electrolyte known as Li6PS5Cl. This schematic outlines a 5-step industrial strategy to process these cells from full stack to regenerated materials. Because the cells are non-flammable, steps A and B involve safely removing the packaging and submerging the intact stack directly into a chemical solution. The solution utilizes a low-cost, low-boiling point polar solvent like ethanol. The ethanol interacts with the thiophosphate units inside the sulfide-based solid electrolyte, causing the solid layer to dissolve cleanly into a liquid suspension. Crucially, while the solid electrolyte dissolves into ethanol, the spent lithium cobalt oxide cathode does not react. It remains completely solid. Now that the cell is split between a liquid suspension and solid particles, the mixture is fed into a centrifugal decanter. The spinning forces cleanly separate the heavier solid cathode precipitates from the dissolved electrolyte. By exploiting the distinct solubility of the inorganic solid electrolyte, we harvest the core components in their original forms without using any toxic acid. Once the ethanol is evaporated, the recovered solid electrolyte is safe, but it suffers a severe electrochemical penalty. The dissolution process reduces its particle size, and its ionic conductivity drops sharply to just 0.11 millisiemens per centimeter. That degradation, however, is entirely reversible once it undergoes targeted thermal annealing. These diffraction and Raman charts compare the pristine against the recovered electrolyte. The perfectly matching peaks prove the physical structure is fully restored. Finally, this Nyquist plot verifies the recycled electrolyte recovers its original ionic conductivity, performing exactly like brand new material. Thermal annealing proves that we can fully reverse the degradation of the solid electrolyte, restoring high-performance conductivity, using a fraction of the thermal energy required by a smelting furnace. That leaves the solid cathode particles we pulled from the centrifuge. After hundreds of cycles, this material is heavily depleted of lithium ions and is coated in an oxidized cathode electrolyte interface, or CEI layer. This schematic traces how we restore the cathode core. First, a simple water wash dissolves the oxidized byproducts, cleanly exposing the degraded particle. Next, hydrothermal regeneration safely injects lithium ions back into the structure, completely restoring the particle to its fully active state. To validate the entire process, researchers built a new cell using only these recycled materials. These performance charts plot the voltage profiles and cycle retention of a pristine battery against our fully recycled battery. The lines overlap almost perfectly. The recycled cell achieves nearly identical first cycle capacities and maintains a coulombic efficiency of over 99.9%. Achieving a 500 watt-hour per kilogram solid-state battery is only half the engineering challenge. True commercial viability demands a closed-loop architecture, where cells are engineered natively for low-energy, direct circularity.